30 voices in the park, 20 leashes, a dozen names called at the same instant, all of them blending into one wash of human sound. And somewhere in that wash, your dog's head lifts, not at the loudest voice, not at the closest one, at yours saying their name. Most owners watch this happen 100 times and never ask the question underneath the moment: how? What is the brain actually doing in the half-second between hearing the noise and finding you inside it? The answer is stranger than almost any owner suspects, and there is one specific point where the whole system suddenly fails. The intuitive story goes something like this. Your dog hears their name, recognizes the word, and looks up. Word in, response out, like a tiny doorbell. That story feels right, and it is wrong, because a dog is not hearing their name the way you do. They are not matching letters or syllables to a meaning, the way a child eventually does when they learn that the marks on a page spell who they are. They are matching an acoustic shape, a specific contour of pitch and rhythm and stress, against a memory of how that shape has sounded in every previous moment of their life. This is why your dog's name still works when a stranger says it. The voice changes, the consonants land slightly differently, the timing is off. And somehow, the brain underneath those floppy ears still says, "That one is mine." The question is, how does the brain pull that off? And where exactly does it stop being able to? This is exactly what Amritha Mallikarjun and her colleagues at the University of Maryland set out to measure. In a 2019 paper in Animal Cognition, they ran 3 back-to-back experiments, 62 dogs in total, a mix of household pets and working dogs spanning every major breed group. The setup was almost cruelly simple. A stranger's voice would call either the dog's actual name or a carefully matched control name, a name with the same length, the same emphasis, the same number of syllables. The researchers measured how long the dog actively listened in the direction of the speaker. In quiet conditions, the dogs listened to their own name for 8.3 seconds and to the control name for 7.2 seconds. A small gap, but a statistically robust one. In a follow-up experiment, the gap got bigger, 7.52 seconds against 5.27 seconds. And here is where it gets interesting. They added a layer of multi-talker babble, the sound of human conversation crowding the test name. At +5 decibels, where the dog's name was clearer than the babble, recognition held. At 0 decibels, where the name and the babble were equally loud, recognition still held. The dogs were pulling their identity out of a small crowd of unfamiliar voices. Then the team kept turning the noise up. At -5 decibels, with the babble now slightly louder than the name, the entire effect collapsed. The dogs no longer preferred their own name over the control. They simply preferred whichever clip happened to be quieter. So your dog can find their name inside a moderately loud kitchen, a backyard, even a small dinner party, but tilt the noise about 5 decibels past their voice and recognition breaks. The signal does not just get harder to find, the shape of it dissolves, which raises the deeper question waiting underneath all of this. If the dog brain can do that much filtering, that fast, what is actually going on inside the brain when it hears a human voice? That is where the picture stops being acoustic and starts being neural. In Budapest, Attila Andix and his team trained 11 dogs, a mix of border collies and golden retrievers, to lie completely still inside an MRI scanner while awake, an act of patience most humans would fail at. They played the dogs nearly 300 sounds, dog vocalizations, human vocalizations, and environmental noises, and watched what lit up. What they found in 2014, published in Current Biology, was the first hard evidence that the dog brain has a dedicated region for processing voices, sitting in roughly the same relative position as the voice region in your own auditory cortex. When the dogs heard another dog vocalize, that region lit harder than for any other sound. When they heard a human voice, it still lit. The voice region responded to species and to emotional valence in ways that mirrored what fMRI had already shown in humans. Then, in 2023, Anna Gergely and her team scanned 19 family dogs and pushed the picture even further. They played the dog's adult-directed speech, infant-directed speech, and dog-directed speech. The brain made a clear distinction. As average pitch went up, and as pitch variability went up, a left-side auditory region responded more strongly, especially to female voices. So when you slip into that slightly higher, slightly more sing-song voice you use only for your dog, a measurable patch of their brain is responding to exactly that shift, not metaphorically, not loosely, measurably. And here is where the whole story should start to feel a little too clean. Because if names are recognizable acoustic shapes and the voice region responds more strongly to the right kind of voice, you would expect any dog to react fully to their name spoken by their owner in any tone at all. That is not what happens. In a 2016 study published in Science, again from Andix and his Budapest team, dogs were scanned while they listened to real praise words and neutral words said in either a praising tone or a flat, neutral tone. The brain split the work in half. The left hemisphere processed the meaning of the word itself. The right side processed the tone. And the reward circuits of the brain, the parts that actually translate into a tail wag and a happy, engaged dog, only lit up fully when the praise word and the praising tone arrived together. Either alone produced something thinner, weaker, almost ignorable. So a name called to your dog in a dead, distracted, half-attentive voice is not really their name in any meaningful neurological sense. It is a sound their brain has to work harder to even register as directed at them. The signal is not the word alone. The signal is the word riding on the right voice. Pull either piece out, and the message arrives in the ears but does not finish landing in the brain. Sit with that for a second. Your voice, specifically yours, with its particular pitch range and its particular way of shaping their name, is not just a label your dog has memorized off a list. It is wired into a region of cortex that was waiting for exactly this kind of signal. The brain underneath their skull has a small piece of real estate that lights up brighter when you, out of every voice it has ever heard, are the one talking. That is a strange thing to absorb when you are watching them sleep on the rug. It also quietly explains something subtler. Why your tone seems to change the second you walk into the house, even when you did not plan it. Why your dog seems to know, before you say a word, whether you are about to leave or about to stay. They are not reading your mind. They are reading a thick stack of acoustic patterns built up across thousands of ordinary moments. Dishwashers running, mail being opened, keys hitting the bowl, and your voice is the through line in all of it. The name is just the loudest pin on the map, which is why a quiet shift in this system is worth paying attention to. If your dog used to find you across a noisy park and now seems to miss the call, do not jump straight to disobedience. Remember the -5 decibel threshold. On a busy street, near a running vacuum, inside a car with the windows down, your voice is regularly competing with ambient sound that close to or above itself. That is not stubbornness. That is physics meeting biology. Exactly as the Maryland team predicted. But if the same dog stops responding to their name in genuinely quiet rooms too, especially an older dog, that is the version of this story that belongs in a vet's office, not a YouTube video. Veterinary behaviorists have long noted that early hearing loss in dogs can hide as selective listening for months before an owner connects the dots. The same neural machinery that makes name recognition feel almost magical is also the first machinery to fade. So, the next time you stand at the edge of the park, surrounded by 30 voices and 20 leashes, and you call your dog's name, watch what happens with new eyes. Inside their head, in less than a second, a dedicated voice region has activated, a prosody region has registered the lift in your pitch, and an acoustic memory has matched the shape of that sound to the only one in the world that means them. 4 neural events, 1 head turn. The simplest moment in dog ownership, the one we barely register, turns out to be the densest. One quiet question, though, before you go. If your voice is wired this deeply into your dog's brain, what happens inside that same brain during the long, ordinary hours you are not home? The answer is its own video, and it is not the one most owners expect.